Hi everyone, we are now going to cover the metapopulation models, both deterministic and stochastic, focusing on a model that has been applied to the UK data. We will quickly introduce the metapopulation framework, then outline its deterministic version before introducing the stochastic version. This coverage is going to be quick because we are already familiar with the compartmental framework such as SIR, SEIR, etc. So the new thing is going to be a few concepts from network or graph theory. Metapopulation is like population of population, so here you can view it as a network of SIR type models. You can also view this video as the continuation of the previous video. There we discussed some applied models that were trying to infer the network of transmission of infectious diseases using social contact surveys. Here we are inferring the network from census data. The code for the model has been kindly made available by the guys, and the data is also freely available, so you can see how these models are fitted in real life. Right, so let's dive in. The best way to view metapopulation is to consider dividing the country into regions. Here we are showing 4 regions for simplicity, but once we understand how it comes together, then extending it to thousands of regions is as simple as changing the upper bound of a for loop in a computer code. For the context, the model we are going to discuss has about 10,000 regions. We can assume homogeneous mixing within each region, and we can thus have an SIR type model within each region. This doesn't have to be SIR though, could be SEIR, SIR with multiple stages, etc. So this is the bit we are familiar with from the previous videos. But now we need to consider interaction between the regions, so we can view the collection of regions as a network, or what mathematicians call a graph. The regions represents the nodes, and the interaction between the regions will be the edges of the network. We can make a variety of assumptions about the connecting edges. One can assume that people in each region are interacting with people in every other region, so this node will have connection with other 3 regions, and we can assume connection in both direction. Network people call it directed graph, and similarly for other regions. Later on, we shall see some examples of alternative assumptions that simplifies the structure of interactions. And the metapopulation model, there are 2 broad ways for specifying the interaction: cross-coupled and mobility. Essentially, cross-coupled assumes that the different regions are connected, say via some invisible force, whereas the mobility approach assumes that the interaction between regions happen due to movement of people. Let's see how these alternatives are expressed in mathematical terms, and let's start with something familiar: the deterministic SIR in terms of differential equations. So these differential equations describe the dynamics of the sizes of the 3 compartments. Beta is the per capita rate at which individuals have effective contact per unit time, and gamma is the per unit recovery rate. We have indexed the equation by I, where I represents a generic region. So for our model here, there will be one such set of equations for each region. To consider the possibility that an infection in region I might be caused by an infective of another region, we can write beta with 2 indices. And now it's quite easy to couple the SIR equations. The summation just reflects the fact that a susceptible in region I may get infected by an infective from any of the regions, though the beta for each region is different, and one would expect higher beta for the infective from the same region. Beta ik represents the per capita contact rate between susceptibles of region I and infectives of region K, and we are summing across all regions K. The equation for the infective is then just the inflows from the susceptibles minus the recovered. We can skip the recovered equation because it's similar to what we have. We can write the beta in matrix form, so this matrix represents the contact rate between the regions, with the diagonal entries representing per capita contact rate within each of the regions. You can see one needs to specify a lot of parameters, n times n parameters. Imagine 10,000 regions, so there's going to be a substantial number of parameters, right? One can simplify the structure in many ways. For example, an easier one would be to say that the matrix is symmetric, so beta from I to j is equal to beta from j to I. This will just about half the number of parameters, so not super helpful. At the extreme, one can say that transmissions only happen between neighboring regions, and hence the matrix will then have a lot of zeros and thus fewer parameters to worry about. As another alternative, one can say beta within each region is the same, and the beta between regions is just a fixed fraction of this beta, which we represent by epsilon. So the matrix reduces to two parameters, beta and epsilon. So a number of alternatives are possible, but one has to make sure that the choice makes sense for the problem one is modeling. So in the cross-coupled deterministic model, individuals are identified with regions, so they don't change regions. But there are some contacts with other regions which result in transmission between regions. And the mobility model, on the other hand, the interactions are explicitly modeled via movement of people. So let's go back to the classic SIR. And the mobility version, there is no invisible force, but interactions between the regions happen via the movement of people, both susceptibles and infectives. So theta ik represents the proportion of people who move from region K to I, and the theta for susceptibles and infectives can be different if one likes. And one can simplify the problem by assuming that only infectives are moving between the regions. The other simplifications that we discussed before are also possible here as well, by the way. By the way, when it comes to determining the level of interaction between regions, one can also use parametric function. For example, when talking about interaction between two regions, Newton's laws of gravity springs to mind, so you can use the so-called gravity model. Masses of the planets become population of the regions. As physics doesn't work in social sciences, one can consider a more generalized version of this equation, include constant in the numerator and denominator, and maybe even make the denominator some other function of distance. And now the econometrician amongst you would have recognized that taking log will linearize this equation, which can then be fitted using regression type approaches. Another variant from physics is the radiation model. So here, Cj represents the number of people who move from region J. The flow of these to I is then proportional to the sizes as in the previous case, but now in the denominator we have P, which represents the number of people that live within the distance between the two regions, excluding the people in the two regions under consideration. So it is not the physical distance between the regions, but rather the density of people who reside in between the two regions that determine the interaction between the two regions. And if one wants to go a bit more universal than physics, then one can assume a variant of power law. A and B here are constant, so the interaction declines rapidly as distance increases. Kim and a few others have millions of friends, rest of us only few, so there's the power law for you at play. Now these are the two broad categories of metapopulation model, but several variations are possible. For the COVID-19 type epidemics, one knows that the epidemic lasts only a few months, and the impact of permanent human migration between regions is negligible over such timescales, so one would expect that the interaction happens via daily commute of people to workplaces or other travels of similar nature, and this is the model we're going to discuss now. Now we have the same regions, but the interaction happens via visitors. So in each region, we have the residents and the visitor from other regions. We represent the number of susceptibles, infectives, and recovered by two indices now. SIK, for example, represents the number of susceptibles who are residents of region I but are visiting region K. So in this region, for example, we have an SIR model for the local and the visitors. So SII represents the local people of region I who are currently in region I, and same for infectives and recovereds. And SKI then represents the susceptibles from region K who are in this region I, and same goes for infectives and recovereds. Say there are m regions in total, then from the region I perspective, there are m minus 1 other regions from which people can visit. So there will be m minus 1 sets of equations for the visitors, but we write only one set for a generic region K. Let's consider the deterministic case first. So we need to represent this in terms of differential equations. We will just write the susceptible as the other equations, then follow similar thinking. And the cross-coupled model, we wrote the dynamics of susceptible compartments for region I as follows. Now we write similar equations for the local residents and the visitors in region I. We assume the contact rate is the same within the region for both locals and visitors. So these guys know that when in Rome, do as the Romans do. So the local residents who are currently in region I will have the same per capita contact rate with the infectious from all regions who are currently present in this region. IKI, remember, represents the number of infectives from region K who are visiting I, and then we also know that people from region I will be visiting other regions. So if we represent the rate at which people leave region I for region K by LIK, then the total number of visitors to all other regions will be as follows. So the size of the compartment reduces by this number, but then people will return. So if we represent the return rate to I from K by RIK, then multiplying the number of people who have gone from I to K by this return rate and summing across regions, we get the returning population, which increases the size of the compartment. Now the visitors to region I face the same force of infection, but the leavers in returns take simple form because they can visit from or return only to their hometown, so we don't have summation. Also, people who leave their residential region K for I increase the population of such people in I, and people who return to K from I reduce the population of such people in I. So that's why the signs are reversed. One can write the product of beta times infectives as the force of infection that a susceptible is subject to, and this is usually represented by lambda. So this simplifies the presentation. And we also note that in alternative form, this is usually divided by n, the total number of people, and the model that we're going to discuss adopts this kind of convention, so we're going to be needing this form. Now we are ready to introduce the model that has been applied to the UK data. You can find the paper that summarizes the model and its results here. It's an updated version of a previous implementation, so you will need to read the earlier paper for technical details of the model. This earlier paper is referenced in the article and is freely available as well. The updated model code, which is in C, can be found on GitHub. Here is the link. The data that the model uses is also freely available. Essentially, it uses the census data, which includes data such as the number of people in local areas, the distances traveled to work. This data is complemented by the National Travel Survey data. The travel surveys are performed on a continuous basis, and the aim is to capture the travel behavior of people, and the data is used here for modeling the movements of non-workers. Now the UK census data is available at local area level. To appreciate the scale of the data set, here is the boundary map of the areas in just London, so you can see it's a lot of data. Across the UK, these amount to a few hundred thousands, which one can use, but these are probably too many. So these guys aggregated the data to electoral wards. Here is the density map of the population by ward from the earlier version of the paper. The different colors represent different sizes of population, so you can see the size of wards vary. Some are more dense than others. And here is the summary of the distances that people travel. So you have two series, one based on census and the other based on National Travel Survey. And before I forget, the workers behave like non-workers on weekends, so they will follow the travel pattern of the non-workers on weekends, whereas on weekdays they'll be going to their workplaces. And summary then, they divided the UK into about 10,000 regions, And then within each region they assumed an SIR model with multiple infectious stages. This could be the exposed, mild symptoms and severe symptoms. To see how it compares to what we saw before, let's quickly draw the SIR model. And we have the per capita contact rate between S and I, and then the recovery rate, gamma. They assume multiple infectious stages, so there are multiple I's now. Each of the infective compartment can infect the susceptibles, but at different rates, so we have a different beta associated with each class. They assume that the infectious classes are sequential, so any susceptible who get infected by any of the infective classes flow to I1 and then go through the sequence of infectious compartments. We can represent the rate of flows from one stage to the next by gamma, so we have multiple gammas. In general terms, we can have n infectious classes and those many betas and gammas. If you don't like the sequential assumption, then you can easily modify the assumption from sequential to, say, parallel. So variations of the SIR are relatively easy to incorporate in this framework. The main thing is to understand how the interaction among the SIRs of the different regions are modeled. Remember, there are around 10,000 regions, so we can have 10,000 such equations, and potentially we have to specify the interaction between these. So that could be 10,000 times 10,000 cross terms. Their approach to interaction is quite simple. As we discussed, this is a mobility-based model where the mobility is modeled via daily commute. So the approach is very similar to what we saw before. Remember, we said that we will have an SIR for the locals and SIR for the visitors. Here, of course, we have a different variant of SIR, and also they model the visitors slightly differently. So we have the workers who spend the night in their residential region I and spend their day in their work region J. Now these workers could be split into the various compartments: susceptibles, which we represent with index 0, and first stage of infection, which we represent by index 1, second stage of infection, and so on. We can represent the workers in a generic infection class C with index C, and let's represent the total number of infectious classes by N as before. And we then have the non-workers who travel between regions, so we represent these by V, and we will then have these distributed into the compartments, and we represent a generic compartment with C. The reason they differentiated between workers and non-workers is that the workers will travel between the fixed places every day, whereas the non-workers will not follow the daily pattern, and hence their behavior will be more random. Things haven't changed much compared to what we have seen so far. We just have an extra dimension in terms of workers and non-workers, multiple infectious classes as opposed to one, and differences in population between day and night, but these are easily summed away. Remember, earlier we wrote SIR in terms of the force of infection parameter, which is just the number of total infectives times the per capita contact rate. Now we will have two infection force parameters. This is because the population changes between day and night. So at daytime, the total number of infectives of type C and region I would be the total number of workers who work in these regions and other non-workers who are in this region because they just like it here. We represented the contact rate of a generic class C infective by beta C, so that's simple. But now we have n classes of infectives. There's no biggie either. We can just sum across the classes. And remember, we said that the SIR can also be written in terms of density, so we can divide by the total population. And similarly, we can write the force of infection at night. We just have to sum across the second index so that we capture all people who spend night in I, but might have spent the day in any of the regions. Well, that wasn't hard. Now we are after the stochastic model, but just for the context, let's see how the deterministic model would look like. Assume we have just one infectious force parameter, just for simplicity. So the susceptible differential equations for workers is similar to what we saw before. Just beta times number of infectives is captured by lambda, and S is replaced by W to the power 0, which is how we represent the susceptibles here, right? The first class of infectives is then just the inflows from the susceptibles minus the outflows to the next class, which is captured by the gamma 1 parameter. The next class of infectives is then the inflows from the previous class minus the outflows to the next. So we see gammas everywhere, and we can write a similar equation for the next class and so on. We can write a similar set of equations for the non-workers, just W will get replaced by V. So I'm going to skip the details and move to the stochastic. The stochastic version of this metapopulation model is also not much different from what we have seen before. So the probability that the susceptible flows to infective compartment 1 over a small interval delta t is just the force of infection times the length of the interval. But here the parameter varies between day and night, so if we represent the proportion of daytime by delta, proportion of nighttime would then be 1 minus delta, so we can just use these to weight the two parameters. And the probability of an infective flowing from one compartment to the next would then be gamma times the length of the interval. Notice this implies the number of events follow Poisson distribution. Here we are assuming the parameters are constant, but as you would see in the latest version of the paper, they are talking about log normal and uniform distribution for the incubation and infectious periods. But this again no biggie. You can just assume these constant parameters here represent a draw from those distributions, so you will need to run this model multiple times, just like one does in Monte Carlo. And we can similarly write for non-workers. Now in the homogeneous stochastic model, we translated similar equation into the master equations and then the Fokker-Planck equation. But here, as you can appreciate, the number of equations is large, so one uses simulation to estimate the quantities of interest. One can easily write the master equation here as well, but these can rarely be solved analytically or numerically, so stochastic simulation approaches are used to estimate the quantities of interest. These could be the number of infectives by region over time. The Gillespie algorithm is designed for simulating such problems, which frequently arise in the modeling of chemical reactions. The algorithm is relatively straightforward, and you can find further references in the article we referenced earlier. But let us know if you'd like us to cover the algorithm. After all, Gillespie does share the pie with us. Now one can extend the approach in several ways. For example, we are treating people in each region as a homogeneous group, but one might want to segment the population by demographic, say age, or risk behavior. And the limit, one can change the granularity from wards all the way to individual level. One can also extend the affiliation in terms of work and other travel to say households, school, clubs, etc. And as we mentioned before, one can also play with various variants of SIR within each region, though as you would see in the papers they published, this is something they have already done. One can also play with the distribution of infectious periods, say log normal, uniform, etc. For the modeling code that they have published, C is fast, but it would be great if you could translate it to object-oriented version either in C++ or Python. And as an aside, remember in the stochastic video, we briefly discussed that the number of susceptibles, infectives, etc. are integer, but if we assume these are continuous variables, then we can write the model in terms of stochastic differential equation, which is easy to handle analytically. A similar analogy applies here. We are treating regions as a discrete variable, but if we let the number of regions increase, so the location becomes continuous variable, and we can write the number of susceptibles, infectives in terms of density across space. Then one gets the system in terms of reaction diffusion equation. So the reaction term captures the fact that the susceptibles react with infectives locally to produce new infectives, and the diffusion terms captures the mobility. The diffusion coefficients for the different compartments could be different, and alternatively, One can also write the continuous version in kernel form. So here we can capture the possibility that the infectives can infect people who are further away, but maybe at a lower rate. This is very similar to the operator form we saw in the R0 video, so everything is coming together. I hope you enjoyed the video and I look forward to seeing you in the next.